Hey up guys, welcome to this video where we're going to take a look at another interesting problem from mathematics, and we take a more careful look at the problem solving process and what that might entail when it comes to trying to find a solution to a non-routine problem. So non-routine problems are exactly the kind of thing that you're going to see on, for example, a mathematics admissions test. So if you're applying to university here in the UK to do mathematics, you may be required to sit the mathematics admissions test, the MAT. And the problem that I've chosen for this video is from an MAT past paper, the 2011 past paper, to be precise. I like MAT papers. I like the problems that are on MAT papers because they're good, challenging problems that really make you think in very new ways, ways that the normal A-level mathematics exams won't necessarily make you think. You've really got to, I hate the cliche, think outside the box. Okay, you've got to think creatively. You've got to be original with your solutions. And you've got to really understand on a much deeper level what it is that you're doing. And it's exactly this kind of deeper understanding that is going to be sought for when it comes to deciding whether or not you will be accepted into such and such a university. What your examiners may be looking for is really the potential that you have to generate ideas and express those ideas for solutions to problems. Don't think, by the way, that everything rests on whether you get a complete and perfect solution to a problem on the MAT. It's nice when you find a solution to a problem, but sometimes just showing that you have potential to develop ideas, that's what your examiners are going to be interested in, because that's something. Because even if you're not in a position at this stage to really fully follow through on your idea, that's something that can be developed. If you've got no ideas in the first place, then you've got nothing to work with. Your professors at university are not going to have anything to work with. Whereas if you're at least generating ideas, then you've got the potential to go on to elaborate, to articulate what those ideas are going to be. If you want to develop some help developing your problem solving skills, if you're preparing for the MAT, if you're preparing for STEP exams, further maths exams, A-level, or just normal maths exams, A-level, feel free to get in touch with me. I've got lots of experience providing one-to-one mathematics tuition for MAT, for STEP, for further maths, and for A-level maths. Many of my students in the past have gone on to do mathematics, data science, statistics, physics, computer science at top universities, including Warwick, Oxford, Cambridge, Durham University, to name a few. If you would like to know how I can help you, then feel free to get in touch. I'd love to have a discussion with you about your needs, your requirements, and tell you how I can help you. And I'd love to see you secure a place at the university that you want to go to. Okay, so let's get on with the problem. This problem is, I'd call this an optimization problem because you're trying to find maximum and minimum values of certain functions. Now, at A-level, when you're doing A-level maths, when you see the word maximum or the word minimum, this usually means differentiation, right? Differentiate, find when the gradient function is equal to 0, use second derivative test if you need to identify what type of turning point, and blah, 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 blah. Unfortunately, that's not going to work here because the functions that we want to find maximum and minimum values for are constrained in some way. Okay, so there's a bit more thought that's required to go into actually finding where the maximum and minimum points are going to be. Differentiation is it's not forced to not work here. It's just it doesn't work. Okay, it doesn't get us the results that we want. Okay, so question number 4, 2011 MAT. I'll leave a link in the description so that you can download the paper for yourself and you can see the problem. I'm just going to read it off my computer screen, which is here just below the camera. So we start out with let Q, that's uppercase Q, denote the quarter disk of points xy such that x is greater than or equal to 0, y is greater than or equal to 0, and x squared plus y squared is less than or equal to 1, as drawn in figures A and B below. So figures A and B are identical, which initially threw me because I thought, why would they present two identical diagrams? The answer to that comes later on, because with one of the diagrams you're expected to do something, to draw something on one of the diagrams, but then you need a fresh diagram to draw something else. So it does make sense. But I spent about a minute trying to figure out what was the difference, like spot the difference between these two diagrams, except there's no difference. So anyway, what we get is effectively quarter circle, radius 1, x, y, there we go, this is our region Q. Okay, easy peasy. So it says, on the axes in figure A, sketch the graphs of x plus y equals, and I've got to get these right, half x plus y equals 1, and x plus y equals 3 halves. Okay, so this is easy, by the way. There's nothing difficult here. So where's my red pen? X plus y equals a half. Obviously, we can think about this as y equals minus x plus a half. We can think about this as y equals minus x plus 1. And we can think of this as y equals minus x plus 3 halves. So we're just drawing some straight lines on here. Okay, there's nothing difficult about this. One is the first one. Hopefully you'll be able to see this, but it's just a straight line of gradient minus 1 through a half on the y-axis, and obviously through a half on the x-axis as well. X plus y equals 1 is a line of gradient, again, minus 1, so it's parallel to the one that we've just drawn, but it goes through the point 1 on the y-axis, or 0, 1, and the point 1, 0 on the x-axis. Y equals minus x plus 3 halves, same gradient, minus 1, and goes through 3 halves on the y-axis. Okay, so on the diagram that you're given, there are some scales, so you could draw these much more accurately. But for what we need to do, this is going to suffice. Okay, what we notice then is that these first two lines kind of go through the region. They intersect the region Q in some way, but this third line does not. That's going to be relevant in a second. Okay, to notice that, because then we're asked, what is the largest value of x plus y achieved at points x, y, and q? Justify your answer. This is important. Justify your answer. So you can't just state what you think it is, even if it happens to be right. So understand that in mathematics, you cannot separate the answer, and I put that in inverted commas, the answer from its justification or its solution, or whatever you want to call it. Okay, so very often in lessons, somebody might do some homework problems or something like that, and for a particular problem, they might just write an answer, and the answer might be correct in the sense that it agrees with whatever answer is given in the back of the book or whatever on the mark scheme. And I will say that for all intents and purposes, that's wrong. Okay, so it might be, because it might be something that requires some sort of justification. And the question that I'm often asked is, well, if this was on an exam, would I still get my marks for the right answer? And my response to that is, well, I don't really know, because arguably it's not a right answer without a solution. But what people think is that the right answer in mathematics just means the thing at the end. That's not the case. In mathematics, the solution and the endpoint is the answer. Okay, so arguably just giving the endpoint when there is a real need for a justification for that answer, just giving the answer, it's not an answer. It's not satisfactory. It might be the right thing according to what's given in the back of the book or whatever, but it's not the right answer. So get into the habit of justifying. This is not just an exam thing. This is not just something that you do on an exam. This is something that mathematicians do. In mathematics, you justify your answer. You don't just give an answer. So if I give you a function, I say, is this function continuous? And you say yes. And that's it. Well, that you could have just guessed that. What is your justification? Now, if you show, yes, this function is continuous because and you show me all of your justification and everything's logically sound, and you've arrived at this conclusion that yes, this function is continuous, that's much better. That's what we're talking about, right? So you've got to make sure that even for fairly straightforward stuff, obviously there's a line that you've got to draw somewhere, but even for seemingly fairly obvious stuff, you've still got to justify it. And by the way, one thing that's a real bugbear for some people, including myself, in some textbooks, as in the worked solutions, some authors will write, "It is obvious that such and such." Now, what you will find is that when an author writes this, the thing that they're claiming is obvious is often far from obvious. It's just that they can't be bothered to work it out. They just can't be asked to work it out or something like that. Okay, so on with the show. So we need to find the maximum value of x plus y in this region Q. Okay, so we can plonk different values of x and y in here as long as the values of x and y are the coordinates, correspond to the coordinates of a point in this region Q, then we're fine. So I would think about this in a slightly different way. Rather than asking what is the maximum value of x plus y, I would say if we set x plus y equal to k, what is the maximum value of k that we can obtain? Now, this might seem like a really trivial kind of restatement and kind of pointless in a way, but actually, I don't think it is. Well, at least not as far as I'm concerned, because it helped me to figure out what to do. It helps me figure out what the solution is to this particular problem. So, in that respect, for me, it's an extremely useful rewording of the problem or rethinking of the problem. For other people, it might not work. If it doesn't work for you, it doesn't work. Try something else. Do something for yourself that does work. But this is just an idea. And the whole point of these videos that I make is not just to give model answers, to just stand here and say, do this, do this, do this, and you get the answer. It's really articulating how my solution came to me, to this problem. So understand that the solutions that I present to you in these videos, unless I specifically say otherwise, are my solutions. They're not solutions that I've just taken from the mark scheme or from the back of the book or something like that. Usually I won't even look at the model solutions, and I will present my solution, even if it might even turn out to be wrong in some cases. I might have overlooked something. If I do present an incorrect solution, please let me know. I do try to check them as much as possible. But we all make mistakes. Hopefully I've not made any mistakes with what I've done for this problem. So you've got to, what I'm trying to do is to explain to you what kind of ideas I was having as I was coming up with my solution to this problem. Okay, so one of the ideas that I had was it's kind of motivated by what's going on here, by the way, is to rethink this as, rather than what's the maximum value of x plus y, what's the greatest value of k that I can obtain, given that x plus y is equal to k? because then I can start to think about this as a family of straight lines, just like we've been doing here, right? So again, this is motivated by something that we've already been doing. Because what I can see is here, if I think about this now as the equation of a straight line, I can think, what happens if I increase the value of k? Well, that just increase it cause it. I can imagine it as this line just kind of moving up a bit, right? So if here we've got k equals a half. If I increase k, I can visualize it as this line just moving up. Okay, the y-intercept is increasing. Okay, but all of the points on this line, on any given line, correspond to a fixed value of k. So here on this line, all of the points correspond to a value of k equal to a half. All of the points on this line correspond to a value of k equal to 1. All of the points on this line correspond to values of k equal to 3 halves. So what I can see then is that if I keep moving this line up, there's going to come a point where it's just gonna, the line is going to be tangent to this region Q. Okay, if I go down any further, if I go down, then that will decrease the value of k. Yeah, there will be points x and y that satisfy that I can plug into this equation. But if I increase the value of k, I move the line up a little bit more, then I'm not going to get any intersection with this region Q. Okay, so remember, we need to be choosing values of pairs of values x and y, which corresponds to coordinates of points in this region Q. Okay, so clearly from the geometrical interpretation that I've got of this, I can see that I need to find when this line, the value of k for which this line is going to be tangent to the region Q. In other words, to the circumference of this quarter circle. Well, that's easy because we've got a symmetry here, by the way. We've got a symmetry in the problem. I could, if I really wanted to, solve the equation the simultaneous equations x squared plus y squared equals 1 and y equals minus x plus k. I could solve these simultaneous equations, or I could be a little bit more subtle about how I think about this and realize that there's a symmetry. It's not, okay, my diagram's not drawn terribly accurately, but there is a symmetry here in the line y equals x, which indicates that this line with gradient minus 1 is going to be tangent to the circle Q at this point when x is equal to y, which is clearly going to be when x equals 1 over root 2 and y equals 1 over root 2. So that means that the greatest value of x plus y is going to be 1 over root 2 plus 1 over root 2, which is equal to 2 over root 2, or even better, root 2. Okay, that's the greatest value of x plus y in this region Q. So that's the first part done. Nice, gentle, steady introduction into the problem. So now we move on to part 2. Let me scroll down a little bit. Okay, so on the axes in figure B, sketch the graphs of. Okay, so I'm going to need another graph. So here we've got Q again, 1, 1, 0, x, y, and here we've got xy equals a quarter, xy equals 1, and xy equals 2. And it's basically the same thing, by the way, but except instead of straight lines, here we're going to get y equals 1 over 4x, y equals 1 over x, y equals 2 over x. So these are reciprocals. So y equals 1 over 4x is just really a sketch that we need. So it's going to look something like that, maybe. Y equals 1 over x. Okay, that's going to be up here somewhere. Again, there's the diagrams that you're given in the on the paper itself that you're expected to draw on, you've got scales and things like that to help you out. So I'm just giving you a rough idea. And finally, y equals 2 over x. Okay, so this is xy equals a quarter, xy equals 1, xy equals 2. So what do we notice here is that, again, some of these curves intersect Q, some don't. Important to notice. Not drawn to scale at all. Don't worry about that. It's not important. What is the largest value of, where are we? Oh, x squared plus y squared plus 4xy. So x squared plus y squared plus 4xy achieved at points x, y in Q. Okay, so it might be worth us just taking note of where this maximum occurs, by the way, where the maximum, and I'm going to do it in a roughly similar way to what I did before. So whereas before I had x plus y equals k, I'm going to think about, rather than what is the maximum value of xy in the region Q, I'm going to think what's the maximum value of xy equals k in the region Q. Okay, because what I realize here is that as k increases, this curve kind of moves outwards. So I'm kind of visualizing the curve just kind of moving outwards. So we don't take it in an overly literal sort of way. It's just an interpretation. Something that is going to help me arrive at a clear understanding of this problem and hopefully bring with it a solution to the problem. So don't necessarily take it too literally. But I see this as an increased k. This is going to move outwards. So if I want to maximize the value of k, when's that going to occur? Well, it's going to occur when xy equals k is going to be, again, tangent to the region Q. And again, by the symmetry, this is going to occur when x equals y equals 1 over root 2. Okay, again, you could kind of solve the equations. X squared plus y squared equals 1, and y equals k over x, and things like this. You could try solving these simultaneous equations if you really wanted to, but it's not necessary if you just make some careful observations and you understand what it is that you're looking at. Okay, so yes, there are all sorts of sophisticated techniques that you can apply that will deal with general situations, but one thing that I really learned from this problem, or that I really had a chance to reflect on, is that even though you have general methods for dealing with certain types of situation, that category of situations is still made up of particular situations. And each particular situation has its own particular features. And sometimes, not always, but sometimes there are some particular situations with particular features that really allow you to bypass all of the kind of general approach. So it's not that the general approach is useless or anything like that. It's just sometimes it's practically a little bit more cumbersome and a little bit more work than it really needs to be. And you can cut back on that in a big way sometimes by just paying attention to the specific nature of the situation that you're dealing with. Okay, so this is important. This is really useful to us, because now we know that x plus y and xy are both maximized at the same point in Q. Okay, in other words, when x equals at the point 1 over root 2, 1 over root 2. Both of these expressions, that allows me to do something here, because now we're looking for the maximum of this expression. And it didn't take me that long to figure out what to do here. In fact, I actually kind of misread the question in a good way initially when I first went through this, because I just automatically found that it doesn't actually ask for it. I don't think. No, it doesn't actually specifically ask for this, but I just, as soon as I'd done this, I found where the maximum is going to occur. So I found where the maximum of xy is going to be. It didn't specifically ask for that, but fortunately I did that, and it kind of triggered the idea, I guess, what I was going to do here. So if I write this as x plus y squared plus 2xy, then one way that I can maximize this expression is by simultaneously maximizing x plus y and xy, which in this case is possible. Not in all cases. This is what I'm talking about. Specific cases, specific features. Okay, so you might ask, well, what if you can't simultaneously maximize these? Well, then you do something else. You're going to have to look for something else to do. But if there is a specific feature that you can take advantage of, do so. Okay, you're not doing anything wrong. Just because it's not something that that holds in general, but holds in this specific case, you can still use it. Okay, so I know that x plus y can be maximized at this point, and xy can be maximized at this point. So therefore, this expression can be maximized at the same point. In other words, I know the maximum of x plus y is square root of 2. And I know that the maximum of xy is going to be half. So what do I get? I get 2 plus 1 equals 3. The maximum of this, therefore, in the region Q is going to be equal to 3. Okay, so now things start to get a little bit more interesting. Okay, so let's go for the next part, which is we need to maximize the expression x squared plus y squared minus 6xy in the region Q. Okay, so here we arrive at a situation, as we'll see, where we can't do what I've just done. Okay, when I had x squared plus y squared plus 4xy, and I was able to kind of rewrite the expression in a particular way such that I could maximize this bit and maximize that bit simultaneously. Can't do that now in this particular case. So this is what I'm talking about. If you're in a different situation, you're going to have to do something different. Okay, it's as simple as that. Yes, there are general approaches. So these are optimization problems, and one technique for optimizing or finding maximum values and minimum values of functions given certain constraints. I mean, there's all sorts of techniques, but a common one is, for example, Lagrange multipliers, which is a very general approach, and it's very useful. But also it does come along with certain problems that in practical settings, it can be very difficult to use. So theoretically, it can bail you out because it guarantees certain results and things like that. But in specific cases, it's actually more trouble than it's worth to apply. And it's maybe better to actually just take a step back and think, is there a more subtle way that, rather than bringing out the big guns, is there something that you can do that's a little bit more subtle? This is just because you have possession of a general theorem, for example, whatever it is, doesn't mean that it's going to be practically worthwhile to try to apply it in all cases. There's plenty of general methods for doing things. So if you go on to university to do maths, there'll be all sorts of general solutions to this problem and that problem and the other problem. But the problem is that these general methods of solution are, in some cases, practically impossible to actually carry out, or very, very difficult to carry out. And really, in practice, you're only able to, so you might have a category of something, of a certain type of problem that you're wanting to solve, and you've got a general method for that theoretically solves all of these problems in this category. In reality, this general approach is impractical to use. Okay, it's a theoretical thing, and it allows you to make certain inferences, which is useful for doing mathematics. But if you're actually wanting to solve specific problems, specific cases, you might find that this general method is just so unbelievably cumbersome as to be just a waste of time, even bothering to try. And what you might find is that in reality, of this category of theoretically solvable problems, there's only a certain subcategory that's practically solvable, and they're practically solvable by using a completely different series of techniques to solve them. So be aware of that. Be aware that sometimes, yes, you might have general methods of solution to certain categories of problem. Don't just automatically go to that necessarily. Just sometimes it's worth taking a step back and thinking, is there something a bit more subtle that I can use here in this specific case? So naturally, when it came to this, one of the first things that I tried was basically what I did before, which was write this as x plus y squared minus 8xy in this case. And I had a feeling that it wasn't going to work. It's very unlikely that in an MAT exam or a STEP exam, for example, that what's worked in one part is going to work exactly the same, symbol for symbol, in the next part. That's not how they organize the exams. It can sometimes they can kind of mislead you into thinking that that's going to be the case. So this kind of resembles what we've just been looking at, but it's sufficiently different for you to have to come up with a completely separate method of approach. Okay, so this doesn't work. Why? Because to maximize this expression, we're going to need to maximize this bit, the x plus y squared, and minimize this. Okay, I mean, I'm not saying that that's not possible to do. It's just, it's not going to be clear from what I've got here how I'm going to do that at all. Okay, I'm not saying that you can't do that. It's just, that's not what I did. So I tried x plus y, x minus y squared, maybe. X minus y squared, what am I going to get here? So I'll get the x squared plus y squared, and in this case I'll need a minus 4xy. Okay, I'm still kind of in the same situation. Maybe I could make this work. I'm not saying, by the way, that these are not going to work, that you can't make these work. It's just I didn't follow through any further with these because there was either a better idea that I had, something that I considered to be a potentially better idea that I went to, or I just thought I'm just going to give up on that. So this, for example, I thought, well, maybe this would be better to try. And then I came up with another idea, which was quite lucky, actually, that I came up with the idea that I did. And that's how it is sometimes. Your brain just gives you ideas from deep down in the back of your mind somewhere, and you've got to listen to them. You've got to be prepared to just act on them and see what happens. So fortunately, I came up with the idea, and I'm not saying that this is the only way that you can do this, but this is the way that I did it. I wrote this as x minus 3y squared minus 8y squared. So it's almost like completing the square on this, as if it were a quadratic in x. Okay? So think about it as something like x squared minus 6xy plus y squared. It's kind of like completing the square. Okay, why did I do this, or why did I find this more useful? well, to maximize this expression, I need to maximize x minus 3y. Now, admittedly, I could minimize x minus 3y as well, because of the square here, for example. I could either maximize it or minimize it, and it actually doesn't make any difference. So I can let's just go for maximize. Okay, maximize x minus 3y or minimize it, because it could be negative. I'm squaring it, so we might get that x minus 3y could be equal to 2. It could also be equal to minus 2, for example, both of which would give 4, which would maximize the square. Okay, but let's just go for the time being, just for sake of argument, that we're going to maximize x minus 3y. But I also want to minimize y squared. Okay, so I want to minimize that I'm subtracting. Well, to maximize x minus 3y, I need to maximize x, and I need to minimize y. Well, minimizing y is effectively the same as minimizing y squared, because what we'll find is that to minimize y means setting y equal to 0, and to maximize x means to set x equal to 1. So x and y are independent, by the way. They're independent, so this is kind of what makes this work, is that I can deal with the x and the y independently. So what does this correspond to? It corresponds to the point x equals 1, y equals 0. That's here. On the other hand, as I was saying before, I could minimize x minus 3y, which is going to amount to me minimizing x and maximize y. The reason that I didn't go for this is because to maximize y would also be maximizing this, which actually turns out to work in this case. Okay, it's just I prefer to view it in this way. Okay, so we'll get rid of that. Okay, so I'm trying to think now. That means that the maximum value of this is going to occur. By the way, the points where the maximum occurs is not necessarily unique. We'll see that in a second. One possible point that I can choose that is going to maximize this expression is going to be when x equals 1 and y equals 0. That's here. And at that point, I'll get 1 squared plus 0 squared minus 0 is going to be equal to 1. That's the maximum value of this expression on Q. Okay, now there's all sorts of ways. I didn't actually, initially, by the way, I didn't go for this. I didn't view it in a purely algebraic way. I went for this in a more geometric sort of way. I got a slightly different result. We'll see in a second. So what I did initially to maximize x minus 3y, I did what we were doing earlier. I wrote x minus 3y equals k. And I thought I want to maximize the value of k. Okay, so what does this look like? This is kind of a series of straight lines, right? I can think about it as 3y equals x minus k, and y equals a third x minus a third. In fact, I'll write it as 3k, just so that we get minus k here. Y equals a third x minus k. So again, I was thinking about varying the value of k here. What's this going to look like? It's a line of gradient a third and y-intercept minus k. So if k equals 0, we're going to get a straight line here, gradient a third. As k decreases, So notice here that it's minus k. As k decreases, as it becomes more negative, this line is effectively going to move up. So I'll get a series of lines, and as k becomes more positive, the line is going to move down. Okay. So where is the maximum value of k here? Well, actually, it turns out to correspond to this line here, to this line at the bottom. That will be, well, when will that be? When x is equal to 1, a third x minus, let me think, when x is equal to 1, 1 minus 3 times 0 is equal to 3, k equals a third. So this corresponds to when k is equal to a third. So that means that x minus 3y is going to be equal to 1. Okay. And the only point of intersection of that line with q is when x equals 1 and y equals 0, which is what I got here. Okay, so that's one way that you can kind of go about this, purely algebraic way or a geometrical way. But also, I've done this. I've rewritten this as x minus 3y all squared minus 8y squared. There's nothing saying that I couldn't have done this. Written it as y minus 3x squared minus 8x squared. Done it from that perspective. And I think I've not actually gone through with the full calculation for this, but for this you would have to maximize y, minimize x, which is going to correspond to this point here. Okay, so this is another point that you might get. So when y equals 1 and x equals 0, that maximizes the value of this in the region Q. So don't think that the maximum value can only occur at a single unique point. There might be multiple points, okay? In which case you take your pick. It doesn't really make any difference. So somebody, one person might take this approach, another person might take the approach that I took before and get 2 different points but get the same maximum value. Neither of them have done anything wrong. They've both done exactly what they needed to do. So the solutions, the point that we're interested in, or the points that we're interested in, not necessarily unique points. Okay, so that deals with that. So then we come on to by the way, I was talking about Lagrange multipliers earlier. I did try to go through this using Lagrange multipliers, this problem. So what it amounts to is maximizing the expression x squared plus y squared minus 6xy subject to. Now, the problem that you've got, the real difficulty is that you've got inequalities involved here. X squared plus y squared is less than or equal to 1. X is greater than or equal to 0, y is greater than or equal to 0. These really complicate things. Lagrange multipliers works quite well if you've got, say if this was just x squared plus y squared equals 1, it's easy. It's much easier. The fact that you've got these inequalities means that you've got to introduce what are called slack variables. So you get a series of simultaneous equations effectively that are just not a waste of time. Just don't do it. But again, it's an example of where you've got a theoretical way of solving a problem that in practice it just creates so much extra work that if you just pay a little bit closer attention to the specific nature of what you're trying to do, you can make your life so much easier. But if you are interested in Lagrange multipliers, definitely have a read about them. They're interesting, it's an incredible result. But as with a lot of general methods for solving a general category of problem, there's got practical difficulties involved. Okay, so on to the final part of this problem. And this I found to be actually more straightforward than the previous parts, to be honest with you. I didn't find too much difficulty in this last part. So nice easy start off. Describe the curve x squared plus y squared minus 4x minus 2y equals k. And when it says describe this curve, you need to describe it in a very precise way. Okay, so rather than just saying it's a circle, yeah, it's a circle, but what's the center? What's the radius? Okay, don't just say it's a circle. So of course we can write this as x minus 2 squared minus 4 plus y minus 1 squared minus 1 equals k. So x minus 2 squared plus y minus 1 squared equals k plus 5. So it's a circle of center, coordinates 2, 1, and radius square root of k plus 5. Okay, easy peasy. So that's the kind of stuff that you did right back in maybe your first term of A-level maths. Really not difficult at all. Hopefully you don't have any difficulties with completing the square and describing circles and things like that. Okay, so then we're asked when k is greater than oh no, sorry, that's part of the previous. K is greater than minus 5. So that just guarantees really that the radius is going to be is going to make sense. Okay, that k plus 5 is going to be a positive number, and we can take its square root. So we need to find the maximum of x squared plus y squared minus 4x minus 2y equals k on the region Q. So sorry, not the maximum, the minimum of this on Q. Okay, so again, maybe a geometrical kind of picture of what's going on, just like we've been doing for all of the previous ones where we're drawing the lines and things like that. What does this situation look like? Or how can we represent this situation? How can we visualize it? So we've got our region Q, 1, 1, 0, and we've got a circle now of center 2, 1. So that's going to be, let's put it about here. That's the center of radius k plus 5. Square root of k plus 5. So as k increases, what happens? The radius increases, right? So for different values of k, we get different circles. And we're looking for the smallest value of k, because remember we're wanting to minimize this expression. In other words, we want the smallest value of k. The smallest value of k. And again, this is why earlier on I was saying that it's maybe useful, rather than thinking about minimizing this expression, minimizing this single number here, which just happens to be equal to that expression. It's just on each of these circles corresponds to a whole set of points. Because if I just look at that, I'm just thinking about points all over the place. Whereas I can set this value of k, say k equals 2, and that will correspond to a whole set of points. K equals 3 will correspond to another set of points. So now, rather than thinking about points as scattered all over the place, I'm thinking about points as being in these concentric circles. Okay, so these I can imagine as k increases, these circles are going to get bigger and bigger and bigger, and eventually I'm going to get a circle that's going to just touch the region Q. And any greater value of K, the circle is going to actually cut through Q. So I'm wanting the smallest value of K such that this circle is going to be tangent to my region Q, which happens to be bounded by a circle, quarter circle of x squared plus y squared is equal to 1. So what do I need to do? I need to find where the point of contact, actually no, I don't need to find where the point of contact is. I just need to consider where that point of contact is going to be. I don't actually need to find the coordinates of it. I need to think about its relationship to the circle over here and this circle here. Well, if I draw a line, if I think about a tangent, maybe at that point, draw the perpendicular bisector, then that not the perpendicular bisector, the perpendicular to this tangent line through this point, then that line will pass through the origin, and it will also pass through, it's not a very straight line, but it will pass through the center of this circle here. Well, I know that the center of this circle is at the point, is at 2, 1. So I know that the length of this line here is 2. So right angle triangle, the length of this is 1. I know that the radius of this is 1, and that the radius of this is the square root of K plus 5. So in other words, I need to, because this is a right angle triangle, okay, I need to, I can set up an equation here that 2 squared plus 1 squared is going to be equal to 1 plus the square root of K plus 5 squared. Okay, the length of the hypotenuse squared is equal to the sum of the squares of the other two sides of the right angle triangle. So this is why diagrams are really useful. Diagrams are always useful. You don't need to draw them accurately, but they can really give you some good insight into how to solve certain problems. Where was I going to go with this? Oh yeah, so then you just solve this equation, and you get, what do you get? You'll find that K is equal to square root of 5 minus 1 squared minus 5. Okay, so I'm not going to go through all of the details. Yeah, even I'm not even sure that you would need to do all of it. Yeah, okay. So this would be much easier. I'll show you how I got to that result. So this is 5 equals 1 plus the square root of K plus 5 squared. So square root each side, you get square root of 5 equals 1 plus square root of K plus 5. So you get square root of 5 minus 1 equals root K plus 5. Square each side equals K plus 5. So K is equal to what I've written on before. Square root of 5 minus 1 squared minus 5. Okay. Easier than it looks to deal with. So that's the smallest value of K for which this family of circles intersects the region Q, and therefore that's the minimum value of this here. I don't need to know the coordinates of the minimum point, by the way. I can figure them out if I really want to. I didn't, because it'd take too long. But that's it. That's the solution to the problem. Again, there might be more general techniques and methods that you can apply to, in theory, solve this problem, but just taking this simplifies. I just thought this simplifies. I'm not leaving it like that. 5 minus 2 root 5 plus 1 minus 5. Oh, that's much nicer. 1 minus 2 root 5. Yeah. Don't be lazy. Simplify your expressions. K equals 1 minus 2 root 5. That's the minimum value for this expression. Okay, that brings us to the end of this problem. If there's anything that you want some clarification on, please feel free to leave a comment in the comments section. I will be uploading more videos relating to MAT and STEP over the coming weeks and coming months. If you wouldn't mind hitting the subscribe button and giving this video a like, that would be great. That brings us to the end of the solution to this problem and the end of this video. Cheers, guys.